Isaac Newton's laws of motion provided a simple and a unifying framework for analyzing motions on Earth and in the heavens. Newton made a conceptual breakthrough by recognizing two different kinds of motion, uniform and accelerating. His laws of motion did something else as well. They defined a force as any phenomenon that causes an object to accelerate. Newton applied this definition to his own studies of gravity, which is an attractive force that exists between any two masses anywhere in the universe. In Lecture 6, I want to tell you about the universal force of gravity. First, we're going to see how Newton's ideas came to define and helped him recognize the force when he saw it. Then I'm going to introduce the mathematical expression for the gravitational force, and I'll try to give you some sense of the intuitive appeal and the quantitative power of this expression for gravity. Finally, I'm going to explore some of the ways that Newton's clockwork vision of the universe has influenced our own perception of our place in the cosmos. Newton's analysis of the force of gravity was rooted in his understanding of the relationship between motion and force. Let's begin by reviewing Newton's three laws of motion. Remember the laws we discussed in the last lecture. Recall that Newton broke with tradition when he defined two different kinds of motion. First of all, uniform motion, which is an object moving at a constant velocity in a constant direction, or an object at rest, sitting on a table, for example. And then the other kind of motion, acceleration, which is any change in either the speed of an object or in the direction of its movement. So unlike previous thinkers, Newton said that orbital motion, perfectly circular motion at a constant speed, is acceleration, not, as previous thinkers had said, uniform motion. And then we have the three laws of motion. The first law states that nothing happens without a force. An object remains in uniform motion unless it's acted upon by a force. And if it's acted on by an unbalanced force, then it will accelerate. The second law puts this idea in a quantitative terms. It says force equals mass times acceleration. And you can plug numbers into that equation and come up with useful conclusions. We saw the power of that equation in the last lecture. And then third, the third law presents the idea that forces act in pairs. Equal and opposite forces occur simultaneously. When you push on an object, it pushes back on you with the same force at the same time. As powerful and as original as these ideas were, they're not in and of themselves the end point in the study of motion. In fact, they're really just the beginning. By defining the notion of force, Newton's laws marked the starting point for the research that continues to this very day in forces and motions in the universe. See, Isaac Newton's three laws define this concept of force, a phenomenon that causes a mass to accelerate. Newton's laws establishes the mathematical framework necessary for identifying all kinds of forces in our everyday life. You just have to look around you. You observe objects as they change what they're doing. They do interesting things. They accelerate. When objects do interesting things, there has to be a force involved. And so you can go and you can look at nature and say, where do I see objects accelerating? And then what's the force involved in that acceleration? During those key years of 1665 and 1666, which saw Newton's remarkable burst of discovery, he deduced a mathematical description of one of these forces, the most pervasive force, the universal force of gravity. Recall that during those years, 1665 and 1666, the bubonic plague had struck England, and that's the period when Newton retreated to his family farm as a consequence of Cambridge University being shut down for those years. And on the farm, he had a year and a half to think and reflect, to ponder the things he'd learned about Kepler's laws, about Galileo's ideas, about other concepts that he had studied as an undergraduate at Cambridge, and he had a year and a half just to think about them. Let's talk about gravity. To Newton's contemporaries, gravity was a terrestrial force. It was restricted to objects near the Earth's surface. But Newton realized that gravity is a universal force. It extends all the way out to the planets, to the moon, to the stars. He realized this while studying in the family apple orchard. The young scholar looked up to see an apple ripening on the tree, and above it he saw the moon in its orbit. Newton's great advance was realizing that it's a single force, one force that's acting on both of these objects. In later years, Newton told friends that this discovery came to him, quote, as he sat in a contemplative mood, and that it was, quote, occasioned by the fall of an apple. Subsequent descriptions have told about the apple hitting Newton on the head, and I don't think that actually happened, but you can imagine the young Isaac sitting there thinking about the universe and how it worked, seeing the apple, seeing the moon, the apple falls. And he says, why doesn't the moon fall? It's up there also, it's just a little farther away. Here's the gist of Newton's idea. You have an apple. It's in the tree. And suddenly that apple breaks loose and it falls to earth, straight down. Well, you could also pick up that apple and you could throw it sideways with a certain amount of horizontal velocity. And if you do, as Galileo tells us, the apple adopts a parabolic path. So when you throw it, it has a curving path. As you throw it harder and harder and harder, the apple adopts more horizontal distance and goes farther and farther. What Newton realized, if you threw the apple hard enough, the apple would go into orbit. It wouldn't stop falling, it would continuously fall, but as it fell, it would move horizontally. So it's falling, but it moves horizontally, and it keeps going around the Earth. That's what the moon's doing. It's going around the Earth, constantly falling, but it has sufficient horizontal velocity to keep it in orbit. Previous scholars had seen these same events. These were familiar to everyone, but they saw them differently. Newton saw them as variations on a single theme. The moon is falling, the apple's falling, objects that you throw are falling. Only when you add significant horizontal or sideways velocity can you reach that orbital situation of the moon. So it is with any planet, with any moon, anything that's orbiting the sun, anything that's orbiting the Earth is falling. This idea was vividly brought home to me with a pulp science fiction story. When I was a young boy, I was probably 9 or 10 years old when I read this story, and I want to tell you the story. As I remember it, the action took place on an asteroid someplace out near Mars or Jupiter. And a few Marines, 3 Marines, were defending Earth against aliens. The aliens had landed on this asteroid, and I believe there were 2 of them, and they had their spaceship on this asteroid. And they had discovered Earth, and they were about to go back to their home planet and launch an invasion against Earth. So these 3 Marines were the last bastion of hope for the survival of planet Earth. 2 of the Marines were big hulking fellows, and they were lobbing their dwindling supply of grenades at the aliens who were crouched behind rocks on the asteroid. The 3rd Marine was a scrawny fellow. He had glasses. He was sitting down. He had a calculator, or probably a slide rule in those days. And he was calculating furiously, scribbling numbers down on a piece of paper. And as the supply of grenades dwindled down to the last 2 or 3, he reached down, he picked up a grenade, he turned the opposite way, and he threw it in the wrong direction. And his 2 colleagues looked and said, "What are you doing? That was one of our very last grenades." And the young Marine said, "Just wait." And you guessed it, the grenade went around the opposite side of the asteroid where there weren't any mountains or hills in the way, landed on the space aliens, exploded, killed them, and the Earth was saved by this little piece of Newtonian mechanics. By the way, I can't for the life of me figure out where this story was published or who the author was. If any of you watching these tapes know, please get in touch with the teaching company and let me know. I'd love to find that story again. It was a very vivid childhood memory. Well, Newton's concept of gravity is simple, it's compelling, but the true elegance lies in the mathematical equation which Newton derived to explain this force. It wasn't just a qualitative description of the cosmos, it was quantitative. He described a force in terms of 4 measurable quantities, 4 variables. The first one is the mass of an object. The second variable is the mass of a second object. The third variable is the distance between these 2 objects. And finally, we have the force, the gravitational force that results. And this is the equation that Newton came up with. He said, force equals a constant, a capital G for the gravitational constant, times the first mass times the second mass divided by the distance squared. That's Newton's equation for the universal force of gravity. Stated in plain English, between any two objects there exists an attractive force of gravity that's proportional to the product of their masses divided by the distance between them squared. Now, Newton used rather complicated mathematical reasoning, and he demonstrated that stable orbits are possible only if you have a 1 over d squared kind of relationship. If you have an exponent less than 2, it leads to a steadily decaying orbit because the force doesn't drop off sufficiently with increasing distance. And if you have an exponent greater than 2, 2.1 or 2.2 for example, it allows the orbiting body to escape because the force drops off too quickly and the body just keeps moving outward. So only with 1 over d squared do you get the exact relationship. Newton's powerful equation reveals that an equal gravitational force is experienced by any two objects. You and the Earth, for example, or the Earth and the Moon. The exact same gravitational force is exerted on both bodies. In fact, when an apple falls to the Earth also falls a minuscule distance towards the apple. And there's a kind of lever law here. If two objects have exactly the same mass, they would fall the same distance towards each other. But if one is more massive, it's sort of like a situation on a seesaw when you have two children that don't weigh the same amount, that the heavier one has to sit closer to that fulcrum point, and the one who's farther away experiences a much larger motion on the seesaw. It's the same sort of thing. So Newton saw that lever arm kind of effect in gravity. Several aspects of Newton's law for gravity have incredible intuitive power. First, gravity in some sort of deep and mysterious way is an attribute of mass. More mass means more gravitational force, and it's in direct proportion. The gravitational force thus bears a relation to mass just, for example, as your buying power does to the amount of dollars that you have in your pocket. There's this direct relationship between force and mass. Pick up an object and you feel the force that it exerts against your hand. And think about mass from this perspective. In a sense, we can describe mass, therefore, in terms of its phenomenology, but we don't really understand what mass is at a deeper level. We can just describe this phenomenon. Now let's look at the bottom half of Newton's equation. That's the 1 over d squared part of it. As the distance of two objects becomes greater, the gravitational force between them drops off. And it doesn't drop off just in proportion to distance, but it drops off in proportion to the square of the distance. That's called an inverse square relationship, and it's actually a very common relationship. You see this many, many times, even though you may not recognize it. In a sense, distance dilutes gravity in the exact same way that distance dilutes the light from a flashlight. Let me show you this situation. You have a flashlight shining on a surface, and it puts out a certain amount of light. Now, if I double the distance, the area of that light, the bright spot, increases. The diameter increases by a factor of 2, but the area increases by a factor of 4. I double the distance, I have 4 times the area, which means the same amount of light is spread out over 4 times as much area. If you had a light meter, the difference between the intensity at one distance and a distance twice as far away would be the ratio of 1 to 1/4, or 1 over d squared. It's the exact same thing with gravity. It suggests that you can imagine a gravitational field, an imaginary array of lines that radiate straight out from any object, and essentially the gravitational force is the number of those lines that intersect between one mass and another. As you double the distance, the number of intersections of lines becomes less. So you can think about gravity in this geometrical way. Even after Newton proposed his equation for gravity, there was one big gap, and that was the numerical value of this capital G, the gravitational constant. This constant is tremendously important. It helps you estimate the magnitude of the gravitational force between any two objects. It also allows you to calculate things like the mass of the Earth and other heavenly objects, and we'll see how that's done in just a second. Determining G is extremely difficult. It's difficult because your experiment has to be completely independent of the Earth's huge gravitational force that swamps out most other measurements. The experiment also has to eliminate any other contributions by stray electrical or magnetic fields, and that's not very easy. After all, slight static electric charge on a comb can pick up a piece of paper. You can have a magnet, which is a very tiny device compared to the entire Earth, and yet against the Earth's entire gravitational force, the magnet picks up objects. It counters the entire pull of the Earth. So if you think about it, gravity is a very weak force compared to some of the other forces that are around us all the time. The most famous attempt to determine G was undertaken 2 centuries ago by the English chemist Henry Cavendish. He was born in 1731 in Nice. He was born into one of the wealthiest families in all of Britain. He was educated at Cambridge University and spent most of his life, more than 50 years, in London performing scientific experiments. Cavendish is said to have been uncommonly shy, especially shy of women, and he never married. There's a story that he once inadvertently met a housemaid on the stairs of his very large home. He was so unnerved by this experience that he had a separate private stairway built just to avoid future incidents of that sort. He died a recluse in a London home in 1810. Of his many important experiments, Henry Cavendish is best remembered for devising a very ingenious method for determining the gravitational constant G. He did this in 1798. He suspended a dumbbell with lead spheres from a wire, such that the 2 suspended spheres were in proximity to 2 much larger lead spheres that were fixed. The slight force of gravity between the large spheres and the smaller lead spheres caused the pendulum, or this suspended dumbbell, to rotate, to torque slightly. Well, Cavendish knew how much torque it took to twist his wire. He measured that twist, and therefore he was able to measure the force of gravity because he knew the 2 masses of the lead weights, he knew the distance between the weights, and he measured that twisting force. So he could solve for G. Substituting that measured value for capital G, the gravitational acceleration of the Earth's surface and the Earth's radius, all into a modified form in Newton's equation, yields the Earth's mass. And I want to do this calculation for you because this is really interesting. You can actually calculate the Earth's mass just by knowing that capital G and a few other simple things. Let me show you one way of doing this calculation. You have to think about the force exerted by the Earth on a mass. Any mass will do. And so you think about the force. Well, from Newton's law for gravity, force equals this mass times the mass of the Earth divided by the radius of the Earth squared, and also with that capital G as a constant. But from Newton's second law, you can do this another way. You can also say that force is equal to the mass times the acceleration due to gravity, because force equals mass times acceleration. And the acceleration due to gravity at the Earth's surface is 9.8 meters per second squared. That's little g, or the acceleration due to gravity. So you have 2 equivalent descriptions of force, one using Newton's equation for gravity, one using Newton's second law, force equals mass times acceleration. Because these 2 equations describe the same force, you can set them equal to each other. So you say mass times gravity, the little g, is equal to mass, the same mass, times capital G times the mass of the Earth divided by r squared. First thing you can do is cancel the mass, the little mass, on both sides. Just cancel them out. And so now we have the gravity G, small g, which is the acceleration due to gravity, is equal to capital G, which we know, times the mass of the Earth divided by the radius of the Earth squared, and we know the radius of the Earth. So you can solve this equation by rearranging it. Solve for the mass of the Earth. Indeed, the mass of the Earth is equal to little g times r squared over big G. Plugging in the numbers, we end up with the mass of the Earth 6 times 10 to the 24th kilograms. The Earth weighs 6 trillion kilograms. And that number comes just from Cavendish's discovery of the value of the big G, the gravitational constant. Cavendish presented this calculation for the first time in his now classic paper Experiments to Determine the Density of the Earth, published in 1798. That paper stands as a great landmark in geophysical science. It might surprise you to learn that the measurement of this capital G, the gravitational constant, is still of great interest to scientists around the world. In November of 1998, a group of 45 physicists met in London to celebrate the 200th anniversary of Cavendish's original experiment. And they also compared notes on several new measurements of the constant. All these workers performed meticulous experiments. They enclosed their apparatus in vacuums. They eliminated all stray magnetic fields and electrostatic fields. They checked and rechecked every aspect of their experimental work. Rival groups in France, Russia, and the United States used modern version of the Cavendish experiment, that is, mass is suspended either on a wire or on a strip of metal, and watched how that wire or strip of metal twisted due to a gravitational force. But there were a couple of new ways of doing it as well. There was a group in Zurich that weighed a kilogram mass on an exquisitely sensitive balance. In one case, they did it with 1,000 kilogram mass just below, sort of a donut-shaped mass, and then they raised that donut-shaped mass and put it just above the kilogram mass, and they looked at the difference in the weight of the object when that 1,000 kilograms was just below or just above the suspended mass on the balance. Very difficult measurement, but they were able to do it and come up with a value for G. Another American group tried a similar approach. They measured the time that it took an object to fall, and you can measure times to millionths or billionths of a second. So if you measure the time it takes an object to fall with a heavy mass below as opposed to a heavy mass above, you get a slightly different time. Again, you can solve for that capital G, the gravitational constant. All of these techniques now yield similar values for G. For the record, the best estimate of G is now about 6.674 times 10 to the minus 11th meters cubed, kilograms to the minus 1, second to the minus 2. So it's a number that people are still converging on, but that's pretty much the accepted value now. Newton's law of gravitation can be used to calculate many useful things. First of all, given the universal nature of the gravitational force, we have to recognize the fundamental difference between weight and mass, and I do want to make this distinction. These terms are often interchanged, weight and mass. Weight is a gravitational force. Weight is the force of gravity exerted on your hand when you pick up something. Weight varies from place to place. It varies from place to place on the Earth's surface. It's different on the Earth. It's different on the Moon. Mass, however, is the amount of stuff, the number of atoms. And mass doesn't vary from place to place. The mass of this object is constant, even though the weight may vary depending on where you are. You can calculate the weight of a 60-kilogram person on Earth, for example. And we just use the expression force equals mass times acceleration. A 60-kilogram person times the acceleration at the Earth's surface, 9.8 meters per second squared, gives you 588 newtons. But you can do the exact same calculation by plugging in to the expression for gravity. Force equals capital G, the mass of the Earth times the mass of the object you're looking at, divided by r squared. And plugging in those numbers, you come with the exact same answer, 588 newtons. Two equivalent ways of calculating the force, the weight of an object. But objects weigh less on the Moon because the Moon is a less massive object than the Earth. And so you can do the exact same calculations and try to determine what is the weight of an object at the Moon surface. Let's do the same thing. For a 60-kilogram individual, what would their weight be on the surface of the Moon? And here you have to know the radius of the Moon, and you need to know the mass of the Moon as well. And those are both two numbers that we have down. So use the same equation for gravity. Force equals mass of the Moon times the mass of the individual divided by the radius of the Moon squared. And of course, the gravitational constant is in there. You can plug in numbers again. And you find out that on the Moon, a 60-kilogram person only weighs 95 newtons. 95 newtons is only 1/6 of the weight of an object at the Earth's surface. You may remember those wonderful pictures of humans walking on the Moon and some of the antics that they displayed, skipping and jumping, and it looked like everything was taking place in slow motion. That's because the force of gravity was so much less, their weight was so much less that they were able to jump higher they didn't accelerate nearly as fast. Only 1/6 the acceleration, so they'd jump up and they'd come down much more slowly. You could hit a golf ball a lot farther on the moon, largely because of the difference in the gravitational acceleration at the surface of the moon, also because there's no atmosphere, so there's no wind resistance to that golf ball. You'd have to have a very large golf course to have a par 5 hole on the moon, but maybe someday they'll do it. I can imagine lunar golf would be a lot of fun. I want to close this consideration of Newton's laws on a more philosophical note. Newton's universal laws of motion and gravity revealed a deep and a pervasive order in the natural world. One set of laws applies both at the surface of the earth and in heavens, on the moon, on the planets, and the stars. These universal laws occur everywhere. They provide a framework by which you can understand many other phenomena, and they provide a unity to the understanding of the natural world. There's nothing special about the surface of the earth in terms of the laws of motion, in terms of the forces involved. Perhaps Newton's greatest legacy is a view of the universe as a place of deep mathematical order, a clockwork universe. The mechanisms can be deduced through observation and through analysis of the natural world. In the words of the distinguished historian of science, I. Bernard Cohen, quote, "The greatest achievement of Newtonian science must ever be the first full explanation of the universe on mechanical principles, one set of axioms, and a law of universal gravitation that applied to matter everywhere, on earth as in the heavens." Who, after studying Newton's magnificent contribution to thought, could deny that pure science exemplifies the creative accomplishment of the human spirit at its pinnacle? What an exalted view of science, and what a transforming view Newton gave to all humans in all different endeavors. The optimistic view that humans could deduce the order of the natural world had a significant trickle-down effect in other human endeavors. During the Enlightenment, which was about a century after Newton, scholars advocated this rationalist approach to all different kinds of human endeavors, to economics, to education, to political systems, to the law. It was felt there must be universal laws that dictated all kinds of activities that humans undertook. Indeed, Newton's first firm statement of this cause and effect relationship in the natural world seems to have pervaded our legal system today. If something bad happens, there must be a specific cause. Whatever bad happens, you can point to a cause, and indeed, you can go out and sue someone, which is what it seems to be these days. But indeed, cause and effect has become part of our way of thinking about the universe. The drafters of the United States Constitution and the Bill of Rights firmly believed that there was a rational system of government that could be derived, that there were laws and ordering to the political system as well. The Bill of Rights and the Constitution thus reflect this optimistic view of order, the attempt that humans could find that order and in fact run their lives according to those laws. Newton's laws even contributed to theological debates. Some followers of Newton, notably the French mathematician Pierre-Simon Laplace, who lived from 1749 to 1827, and about whom we're going to hear a lot more in Lecture 34, he even speculated that since the laws of motion are exact and they predict the motions of every possible particle under every kind of force and interaction, that if you knew what every particle was in terms of its position, in terms of its momentum, its velocity, of the forces acting on it, that indeed the future of every particle in the universe was preordained. And this led to a very interesting theological speculation. Is it possible, since everything in the universe is preordained, that there is no such thing as free will? That we act out our lives, that every event in our lives, that my standing before you today and delivering this lecture was something that was preordained just by the way particles were set into motion billions of years ago before anyone had ever heard of Isaac Newton and his laws of motion. This idea, by the way, has been silenced by more recent findings of inherent uncertainties in the natural world. Let me summarize this lecture on the universal law of gravity. We've seen how Newton's laws of motion provided a framework for identifying forces in nature. And then Newton went on himself to focus on this force of gravity that you could see everywhere. Gravity is a force that operates between any two objects anywhere in the universe. The magnitude of the force is proportional to the mass of the two objects. It's inversely proportional to the square of the distance between those two objects. And the universal gravitational constant, g, provides the appropriate scaling factor. In the next lecture, we're going to see how Newton's legacy extends to the concept of energy.